All right, welcome to Intro to Machine Learning 1, Lecture 0. This is a Northeastern University course called DS 4400. I am Professor Wu, so let's get started. In machine learning, we often use various functions, different functions, to describe various natural phenomena. Right? And the way you can look at a function is that you have some kind of input, you put some input into this function, and then it gives you some kind of output. So that's one way to view the function. And very often we let function be some kind of mathematical thing where you put a number and we got a number out. So here's an example of a function where you have f of x is equal to this thing here. Now, similar to what we just said, if we put a number 0, right, we're going to get 0.2. So if we put a 0, this function is going to give us 0.2. If we put like 1, all right, then this is going to be 0.5. So basically, you can put any number you want in here, and the function will give you some kind of output. As I said, so this is one way to visualize functions, that it's a system, you put something in, you get something out. Another way to visualize functions is through the usage of plots. So this function here can be plotted as the green line. As we previously discussed, if we put 0 inside the function, then we're going to get 0.2. If we put 1 inside the function, we're going to get 0.5, right? 1 and 0.5. So essentially, you can put a lot of numbers in, and you're going to get different numbers out. And these numbers could be plotted out as this green line over here. So this is another way to look at functions. Hmm? So that is what a function is. And an associated concept with function is called a derivative, or the slope of the function. So when you're talking about derivative at a given point, what it's saying is if you have a positive derivative, like derivative is the number, if you have a positive derivative like this point, it's saying that as x increases from this point, as x increases, the function's going up. That's what that means. So the derivative tells you that as x increases, if the function is going up, or it's going down if it's a negative value. So the sign of the derivative tells us where the function is going. Now, this is important for various reasons. For example, if you are modeling stock market, right? If you get the sign wrong, you that whether it's positive or negative, you're going to buy at the wrong time, right? You want to buy when it's going up, not when it's going down. So the derivative tells you the going up and down. Now, the the derivative tells you goes up, but the magnitude of the derivative. So if you can have a derivative that's positive 0.001, so this is a small derivative. Or you can have 100. Now this is a much bigger derivative. And this is saying that tells you how strong it's going to go up. Is it going to go up a little bit or is it going to really shoot up, right? A big number is an indication that it's shooting up very fast. So we can calculate the derivative at any given point. So if we have a function f, this is a function, right? We can get a function as a derivative. So if you symbolically write this, this is saying that we're going to find another function. The other function is going to be df dx. This is a function. This is also a function. Okay. So this is a function, the original one. This is a function such that you can plug x in any single point. You plug it in and it gives you the derivative at that point. So at certain points, it's going up fast. Certain points, it's not going anywhere. And the way you can do that is once you find the derivative, you plug in a point, and this is telling you at this particular point, it's not really going up or down. Instead, it's just staying flat. Therefore, this particular point, the derivative is 0. But at this point, it's going up like pretty fast, right? It's going up pretty fast. So you're going to get a much larger positive derivative. Certain points, like here, right? The derivative is going, the function is going down. Therefore, at points like this, the derivative is going to be negative. Okay. So when you find the derivative, this is symbolically what we mean. We're taking the derivative of a function with respect to x. Of course, you can be with respect to any variable, but x is like a common one. Once you take the derivative, we can symbolically represent the derivative function either this way or this way. This is f prime, this is df dx. This right here is kind of assuming you know that it's x. This one right here is like explicitly saying that x is the variable. So if we take the derivative here, right? Let's say this is the function that we just saw. That's this green line here. If we take the derivative, right? For those of you that knows how to take derivative, you're going to get another function. And this tells you a function to calculate the derivative at any point x. So this derivative here, if you plug 0, right, it's going to say the derivative is equal to 0, which means at this particular point, the function is not really going up or not going down, right? If at this point, if you draw like a line that just touches this line is going to basically stay flat and not going up or not going down. So the derivative at this point would be 0. But a derivative at this particular point, if you plug 1 in here, that's going to give you 0.6. So this is much larger than 0 and telling you that this function is positive, therefore it's going up, and it's going up at the speed of 0.6. What does that mean? Let's say you have 1, right? If you increase x by 1, so from 1 to 2, if you go from 1 to 2, it's saying that it's going to increase in the y direction by 0.6. So if you go by 1, it's going to go up. If you go to the right by 1, it's going to go up by 0.6. And you can see this point is 1.1, this point is 0.5, the difference is 0.6. So that's what derivative is telling you, that how fast is going up, how fast is going down. So I just showed you, if we plug 1 in, that's what that means. So the key takeaway, why do we care about derivatives? We care about derivative because it tells you that any given point, how fast is the function going to go up and it's going to go down. Okay. Now, that was a function with just one input and one output. There are times that you're going to need multiple inputs. So this particular case, you have 3 variables, x1, x2, x3. And these 3 variables, when you plug it in, you get one output. So this is an example of 3 input and 1 output. So functions like this, you put 3 numbers in, right? You calculate the result, you get 1 number out. Other functions, such as this one. So this looks like 2 functions, but it's like a system of multiple equations. Here, you're putting 3 numbers in, and you're going to get 2 numbers out. Okay, so this is 3 input, 2 output. All right, x1, x3, right? If you plug this in, you know how to calculate this number. If you plug this in, you also know how to calculate this number. So 3 input, 2 output. And then when you take derivative, because you have 3 variables, then you need to have the derivative with respect to the first variable, x1, derivative with respect to the second variable. Again, derivative with respect to the third variable. So this tells you that you have 3 dimensions, right? And in each dimension, how quickly the function is going up or going down. So previously, we saw just one dimension. That's easy. In that one dimension, it could go up and down. But in multiple dimensions, you can also see that in this particular dimension, right, as x increases, is the function going to go up and down? So we have spent basically this whole time talking about derivatives, right? So why do we care so much about derivatives in machine learning and data science? Like, why do we care about it? Well, it's actually one of the most important thing. And let's look at an example. Probability of you getting cancer. Okay, let's say we have three molecules that we can measure from your body, like your blood specifically. And we can essentially take these three molecules and predict the probability of you getting cancer. So we're going to call these three factors, right? X, which consists of factor one, x1, x2, x3. They're just symbolically representation of these three factors. And we have a function that spits out the probability of you getting cancer, right? Right now, let's just assume this x function is magically giving us. But the whole point of this class is actually how do we learn to find this x, right? Once we find this x, then we can make predictions. But let's assume right now we have this given to us. Once we have this given to us, like we take one of you, right? Let's assume you, we take your body and measure these three markers, these three biological markers. And we got these numbers 239. And when we plug these three numbers into the function, it spits out a 97% chance that you will get cancer in your lifetime, which is actually not a surprise because most of us will get cancer. So it says 97%. Okay. So we just took X and plug it into f of X, and it give us an output of 97%. Now, what happens if I take X, instead of plugging into the function, I plug in this? What does this tell us, right? So I plug the numbers we measure from your body, and it give this. Think back to the last like 2, 3 slides we just had, right? What is the point of derivatives? Like, think about it. And once you understand the purpose of derivative, then you can start understanding what this is telling us. Okay? So take a moment. Now the next step is, let's say you have three different drugs, right? And these drugs, the three of them, can individually increase X1, X2, or X3 factor. Given this information, which drug should you take if you want to lower the cancer rate? And which drug should you take if you're, trying to die? So, so I would like, if you don't get this immediately, you want to pause the video, go back and watch it a couple times, and then really, really think about what the derivative is telling us in this particular situation. So, why do we need derivatives? Let's go back to this particular thing. We can see that if we take the drug, now remember, the derivative tells us if we increase this particular factor, right? A positive derivative is going to increase the output of the function. So the output of the function was the probability of cancer. So if you were to increase the first factor, it's telling you that you are going to decrease the function, the probability is going to decrease by this tiny little number. However, the second factor, if you were to increase, right? If you were to increase X, it means that it's going to have a negative effect, -6. So it's going to go down by 6. So this is going to decrease your probability. And the third one is, at your given point, if you were to increase X, it's going to shoot up the probability by a lot, like 20. So from here, I hope you can see that while the function itself, just the function, tells us the probability, the derivative of the function tells us what to do. right? And since machine learning, data science, it's all about taking data and decide on what to do, right? Like you're trying to extract like specific information about the data. Like therefore, like 99% of machine learning, I dare say, are basically just manipulating the input of some function and then it give us some to give us some kind of ideal output. So we have a function, and we're essentially identifying the input that give us the output that we're looking for. Okay? So how can we do this? How can we do anything in machine learning without knowing how to take derivatives? Well, you kind of can't. So this right here is kind of shows you the point that if you don't know how to do derivatives, um, like it will be very hard to understand what we're talking about. Okay, so, well, the design of this class. The probability to take the ability to take the basic derivative is so important. It's so important that without it, this class would basically make no sense. I make the analogy that it's like taking a Shakespeare class without knowing how to speak English. Okay? That's how difficult it is to understand anything, right? So so beyond just learning to take derivative, which is part of calculus. Without knowing how to do calculus, well, you actually need to know a lot of other things too to truly understand machine learning, like calc 1, 2, 3, linear algebra, probability, stat, and you should probably know how to do programming. And this is a high bar. This is a lot of math courses just so that you could truly understand machine learning. Now, this is a high bar, and therefore it is very difficult for non-math majors to break into machine learning. And since Curry, well, we really believe that machine learning and data science are going to be the future, right? Setting this high bar means a lot of CS students won't be able to take the class. Therefore, we need some kind of class to essentially give the student exposure somehow without requiring all these. Okay? Even if they don't know calculus, linear algebra, Python. Ideally, you do know it. However, if you don't know it, this class was particularly designed with that in mind, right? We are all going to know different things. So this class is designed with this in mind, and therefore we're going to try to cover these materials. Now, of course, it will be impossible for us to cover 5 topics in just a couple days, right? That's not possible. But what we could do is to basically cover the bare minimum to give you just the idea. Like a lot of it is basically you get the point and there's a lot of details that you would need to learn. But once you get the point, the details you will have to like catch up. But getting the point is perhaps the key. So, with derivatives, for example, the main point I want you to take away is that, well, you have a function, and somehow you can find the derivative of that function. What I want you to take away is why do we want to do that, right? Once you know how to do that, there's like a bunch of rules that teaches you how to do it, but you need to know why. Okay, so for students that already know these topics, this will be a great refresher because just because you know how to do some of these, it doesn't mean that you get the point. So I dare say 99% of the machine learning are just dealing with derivatives. Okay, so first and foremost, what you need is you need to be able to look at a function and get another function called a derivative function. And like I told you, like the cancer example we saw, the ability to do that is not 100% necessary, but it really helps you to understand what's going on. Okay, so our goal is to basically today we're gonna go over the basics of how to go from the function to the derivative function. And for the most part, it's not that hard, right? There are only a couple rules. If you know these rules, we're going to go over 7 of them. If you know these rules, you basically can take derivative for most things. And the 7 rules are not hard. Like I know like calculus made it very complicated, but we're going to skip a lot of details and just look at these 7 rules. I mean, obviously there are more than 7 rules, but I think hopefully we can quickly go over them so that you can get the point. So the first rule is called the constant rule. The constant rule is when you have a function of some variable x, but that variable is not there. It's just some constant value like 0.2. In this particular case, you can see that if it's just a constant value, 0.2, then all we have is a line, a horizontal line. Well, we just discussed the meaning of derivatives, right? It's saying that at any given point, is the function going up or going down? With a horizontal line, obviously it's not going up or going down. Therefore, the derivative of a constant value is always 0. All right, so a constant value will always be 0. Here's some examples. Derivative of the number 3. Well, that's going to be 0. Derivative of c. Well, c is a constant because the variable is x. So if the variable is x, then as long as it's not x, it's treated as a constant. So you're going to get a 0. Over here, the variable is x, but the value is x, but the variable is y. Therefore, x is not a variable, x is a constant, implying, again, 0. Over here, once again, we have x1 as the variable, but what we have is x2, x3. So they are treated as a constant, hence 0. The constant rule is once you pictorially understand what's happening, right? Whether the function is going up or down, you can see that any constant value, the function is not going up, implying that the derivative has to be 0. So that's the constant rule. The next one is the power rule. If you have a function of some kind of power, so in this particular case, you could power 3, but you could be power 4, power 5, whatever, some kind of power. So the power rule, right, has only 2 steps. Is if you have power rule, you take this number and you put it down here, multiply. So 3 multiply, and you subtract this by 1. That's it. That's it. You pick, let's say this one. Right. Now what you want to do is move this down. Therefore, it's 5, 2x, and then subtract by 1. So that's pretty easy. So over here, the power rule from this is you're going to move the 3 down and subtract the value by 1. So the derivative, right? So the derivative of this is equal to 3x 2. Now, with this, you can find the derivative at any point. So let's do some examples, right? So this x itself is really power of 1. Therefore, you move 1 down, and then 1 minus 1 is 0, yielding us a 3. Like x to the 0 is just equal to 1, right? So that's how we get a 3. Here's another example. We move 4 down, like I said, and then you subtract this by 1, giving us this. Over here, y is the variable. Therefore, x is a constant. So if you move y, this is y power of 1. We only get an x. Over here, x1 is the variable. Therefore, these are all constants. So all you do is move 2 down, right? And 2 minus 1, which is just equal to 1. So the power rule is, this is it, right? The next one is the sum rule. Okay? The sum rule is if you have summation of multiple variables. When you have summation, the rule is very easy. You just take the derivative of each individual one and then add them back together, right? You do them separately and then add them back together. So over here, we have 4 terms. So over here, we can just look at this alone. This is the power rule. This one, power rule, and this one's a constant rule. So you can see power, constant. Okay, so here are some other examples, right? This is a constant, and this just give us 5. Over here, x1 is a variable, x2 is a constant, that goes away. So this give us 2x1, this give us 1, using the power rule. So you want to go over these examples. So this is the power rule together with the sum rule. Okay? So far you've only really learned the power rule. The constant is pretty easy. The power rule you need to remember, and the sum rule is just saying that you have multiple terms. You just do them individually. Here's a quick example. Let's say we have this green line, right? This green line that we've been looking at. Now, this green line here, when we want to take the derivative, well, we can use the sum rule. So this is a constant that goes away. And using the power rule, it's just 2 times 0.3. That's how we got 0.6. Okay? And like I said, you plug 0 into 0.6, you get 0, right? Because at this point, the function is not really going up or down. The next one we have is called the product rule. The product rule deals with function that looks like this. Now, you can just multiply this out, right? So one way to do it is you treat this as a function, ax, bx, and you actually multiply them out when you're taking the derivative. So this becomes 4x third, and now you can just use the sum rule. So that's one way to do it. Another way to do it is to treat them as two functions separately. So if that's the case, the product rule says the derivative of the product of two functions is the derivative of one times b, and then a times the derivative of b. Right? That is the product rule. And this very often, if this is very big and complicated, you don't want to like multiply the whole thing out. It's much easier to treat them as separate. Okay? So if we were to treat a, right, here's a and b, we can find a derivative of a, which is equal to 2. It's pretty easy to find a derivative of this. And then we can find a derivative of b, which is 4x. This is also based on the power rule we just learned. Okay, now therefore, if we use the product rule, where you have a prime times b, b times a times b prime. So we just plug all of them in. A prime, it's right here. B, a, b prime, right? So we plug them in, and voila, we have the result, which is exactly the same as if we had just multiplied them out in the first place. So whichever is easier, that's how you want to do it. So let's take a moment and see if you can essentially solve this problem. Pause the video, or if you are in class, you can just give it a try. This requires us to use the product rule, by the way. You want to use the product rule here. So okay. Hopefully you paused the video and tried it. Now, with the product rule, you need to find the derivative of each function individually. So what is the derivative of a prime? If you use the power rule, 3 goes down, 3 goes down, 3 minus 1, giving us 6x squared. Now, if we use b prime, right, so this right here is also the power rule. You have minus 1, so you minus 1 goes down, and then minus 1 again, giving us minus 2. So it's 1 minus 1 over x squared. So what was the product rule? Well, the product rule is a prime times b, b times a times b prime. We plug all these in individually, and the result is 4x. So hopefully you were able to get this. Okay. Now the next one is exponentials. The exponential symbol, which is e, is a special number, which is approximately this number, 2.71 something. It's analogous to pi. Like most of us are more familiar with the concept of pi. But e is just, another number. And sometimes we often see this exponential function that looks like this, the e value to the x, or also written as this. Now, when we want to take derivative of this is very, very special. It turns out that the derivative of this is just itself. So it doesn't get easier than that. When you have like exponential functions and you want to take derivative of them, you do nothing. Yeah? So this is really easy to remember. The next one is logarithmic. So what does that mean when we have a log function? Well, we take a log of this, right? What's happening is we take the base value. This is called the base value. And then if you do the base value to the y, base value to the y, it is equal to x. So you see how this is kind of like taking the power. Okay? So the base value could be anything. You could pick e, for example. If you have e as the base value, then have e to the y is equal to x. Right? So this is the relationship when you see logarithmic. It's some kind of power relationship. Okay? Now, when the base value happens to be e, we call this log has a special name. It's called a natural log. So instead of log, we often just write ln of x, natural log. And the derivative for the natural log, if you want to take a natural log, is just 1 of x. So this is also hopefully not that hard to remember, right? So, and then one of the thing you need to know is that log of any base is simply the natural log divided by log of the base. So if you know this is just a number, right? Log of 4. This is just a number. So when you take the derivative of log of anything, right, what you do is you rewrite this into the relationship of log. And since this is just a number, right, and derivatives, you can just move constants to outside. So you're really, really just taking the derivative of log of x, which I just told you how to do. So this is how you would do it. So these things, none of them are really hard. A couple things you need to remember, and once you get used to it, it's not that bad. Now, believe it or not, we're already at the last rule. This is called the chain rule, and this is probably one of the most important and more difficult rule, right? Chain rule. So let's say we have some kind of function that looks like this, and we want to find a derivative of this function. Now, this is to the fourth. So you have to multiply this over and over and over again if you want to get like multiply them out, right? And this could be annoying, and you don't want to do that. So there's an easier way to do it, which is the chain rule. With chain rule, we are going to let this thing here called g. So g is just some other function. So it's a subset of the function. So we have this function, and we broke the inner part as just another function. So if we have g, then we know how to find the derivative of f with respect to g with the power rule. So this is pretty easy. If you find the derivative of f where g is the variable, then it's just 4 comes down. So 4, and then 4 minus 1, right? 4 comes down, 4 minus 1 is 3. So we know how to find this with respect to g. Now, g, if we just look at g by itself, we can find the derivative of this with respect to x, right? So finding the derivative of this with respect to x, dg dx, is also really simple, which you just use the power rule and the sum rule, giving us 2. Okay? So if we want to find df dx Knowing how to find dfdg and dgdx, well, we can just multiply them together, right? Notice dfdg times dgdx, the dg's cancel out, resulting dfdx. Okay, so in this case, we have dfdg, dgdx, and voila, we got the results. So the chain rule is essentially a way to allow you to break big functions up to have functions inside functions. And once you do that, you end up getting an easier expression. And you can take derivative of the easier expression inside each other. Like, and then when you multiply them back together, they get canceled out. So that is the chain rule. And that's it. Those are the main 7 rules you really need to know. So over here is an in-class practice. Let's hopefully you'll be able to take the derivative of this, pause the video, give it a try. It's not that bad. Okay. So of course, knowing how to take derivative is important. And in real life, however, like in real life, when you work, there isn't like a magic solution book, right? You if your boss says, find a derivative function for this particular thing, that means nobody's done it. They want you to do it. And when you take the derivative and get a function, how do you know that you're right? Right? Because there isn't a magical solution book out there. And yes, you can actually verify your derivative programmatically. And so that's going to be very useful. Like in real life, you need to take derivatives and you need to verify your result to make sure you know what you're doing. The solution is to use Python. And with Python, which is kind of like a calculator, I have written the code for you on a simple example. And based on this example, you should be able to apply it. So there's this library called AutoGrad. You will need to download this. But once you've downloaded, here is the function we just looked at. This was the practice function. And I personally calculated by hand. So this somebody told me to solve this, and I said, I think this is it. And now I want to use the code to verify. So the way you can do it is I put in the function itself. So here's the function. This is the function that was given. And then this is the function I calculated. This is theoretical. Theoretical. So if I did a good job of finding this function, which I wrote out is this, then this theoretical should be approximately the same as the computational. So this right here, grad f. So you put a function and put into grad f, it will automatically give you the gradient. So this is df dx. So this right here is a programmatic way of finding the derivative. Okay, so this allows you to find the derivative. And once you have this, what you can do is you can just randomly generate a bunch of x and compare the result of your theoretical result that you took the derivative versus the automatic generated. And if you did a good job, in theory, you should get the same values. Okay, so when you generate a bunch of random ones, they should all be like roughly the same. So this will verify that you know how to take the derivative, you got the right answer, and programmatically it concurs with what you calculated. Okay, so this is in real life. Like make sure you go over this, right? This is very, very useful. Okay. Now, derivative, you go from f to f prime. That's derivative. Now, there's another thing called antiderivative, where you're going kind of backwards. You're doing the backwards of derivative. Well, we learn a bunch of rules to take the derivative. Right? We need the derivative because we want to know if the function is going up or it's going down as x increases. So that's the reason. But it turns out if you take the derivative backwards, Like, we're not going to go over why, but it turns out that if you take the derivative backwards, it enables us to find the area under the function. So let's say we have this function here, and we're trying to find the area between point A and B, which is 0 and 2, right? This is the area of a triangle. Now, if you want to find the area of a triangle, hopefully from SATs, you learn how to do that. But in calculus, you can do that when you take the inverse. You do the derivative backwards, okay? And the way we would mathematically, symbolically represent what we just said is right here, this function is 2x, okay? So what we are doing is we have 2x, and we want to find the area between A and B. So symbolically, that's what this is telling us to do. And A, what was A and B? 0 and 2, right? 0 and 2. So we're trying to find the area. So when you see this, this is symbolically telling us like that we are trying to find the area of this function between the 2 points 0 and 2. Now, how do we go about doing that? Well, to this whole process here, right? The process of solving this thing is called integration. So when we talk about integration, it's saying that we're trying to find the area from point A to point B. And the result of doing this is we're finding the integral. So we have this function f of x, and we're trying to find the integral of f of x. And that's telling us we're finding the area under the curve, right? Since this area is a triangle, right, from over here is 4, over here is 2, you can calculate the area pretty easily, which is 4, okay? So we know the area from the fact that it's a triangle, but let's see if we can get the exact same result by using integration. So now we're doing integration, right? So what's happening when we're taking the opposite? Well, what we are saying here is this 2x, this is f of x. And we're saying that there's a function, capital F of x. If we take the derivative of this, it should give us this. Okay? So if we take the derivative of this, it should give us f of x. So this is f of x, and we want to imagine something, some other function, such that if we take the derivative of that some other function, we'll get the f of x back. So this requires you to think of derivatives backwards. And when you do that, when you think of derivative backwards, it turns out that, notice if you take x squared and you take the derivative of that, right? Let's use the power rule. X squared, you moved 2 down, and then you minus 1, which is 2x. So notice how this is exactly the same as the function. So when you take the derivative backwards, we get x squared. After you take the derivative backwards, all you have to do to calculate the area is pick the 2 points, right? The 2 points is 2 and 0, and you just find the difference. That will give you the area. So take the derivative backwards, you get you get the capital F, and then you just plug the 2 points you care about. And guess what? It did give us this exact same area for. Okay? So the key takeaway here, there are two key takeaways. One is that derivative tells us if a function is going to go up or down. The second one is that when we do the derivative backwards, which is called integration or integrals, between 2 points, it tells us the area of the function. So derivative tells us function going up or down. Opposite of derivative, antiderivative, is called integral, and that tells us the area under the function between 2 points. Now, of course, you can also verify integration. So over here, you simply define the function. Remember, the function we're working with is 2x. Once you have this, all you do is you need to make sure you import quad. Once you have quad, you just call the function f, which you define between the points 0 and 2. And guess what? When you print out the area, a, which is the area, give us 0. 0.4. So we just confirm the result three different ways, right? First way is we just calculate the area of a triangle. The second way is through integration. And the third way is to using programmatically to get the integration. So these three ways allows you to essentially confirm. Now, of course, this triangle is really easy. That's an easy example. I could have given you something like this, right? And the area under this will be much more complicated. So let's try to consolidate everything we've learned. Given the following problems, right? You let's see if you can find a derivative of these as well as the integral of this one. Now, this particular function is the green line right here. So you're trying to find the integral between 0 and 1, right? So you're finding the derivative of this. Now, this is much harder than a triangle, right? How do you find the area? Because this point, these are much harder areas to find. Now that you know how to do this backwards, you can now essentially calculate the area. Okay. What I want you to do in class today is to solve each of these problems by hand, right? And then essentially use Python to verify. And I think that's it for today. Okay. Good luck. I will see you next class.